Hi, this work is a joint work with Julia Chusoy, and my name is Tachapon Saranurak. This is about deterministic algorithm for decremental shortest path. So in this problem, you are given an undirected weighted graph G that undergo a sequence of edge deletion or deletion only, all right? And let n be the number of vertices, m be the number of initial number of edges. The goal is to maintain a data structure supporting the following queries. First, a distance query. Given u and v, you want to return an estimate of the distance between u and v. And path query, that is just as similar, but now you need to return an approximate shortest path from u to v. And what we want to do is to minimize the update time. That is the total time to process the whole sequence of deletion, and query time, which is just the time to support distance or path queries. In the single source shortest path problem, SSSP, the query will be between a fixed source S and some vertex V. And for all pair shortest path, APSP, the query can be between any pairs. And now the goal of this work is really to remove something called the oblivious adversary assumption. In this assumption, it says that the whole sequence of updates is just fixed from the beginning, and it's just completely independent of the answer of the queries. So that is a strong assumption, but with this strong assumption, near optimal algorithm are known for both SSSP and APSP. Without this assumption, the state of the art is just much slower. And what we want to do is to remove this assumption, but still make a fast algorithm. And why this is interesting, one reason in theory is this. If you have decremental APSP or SSSP or APSP that works against adaptive adversary, that is, it doesn't assume the oblivious adversary assumption, then there is a known connection that gives us some flow or cut algorithm. So that's the nice application. And indeed, our result is to make progress on this problem against adaptive adversary. And this is because all of our algorithms are deterministic, which automatically work against adaptive adversary. So the first result is on single source shortest path. The point of this result is to get an algorithm that is faster than the classic MN bound. Still, it can both support path query and edge deletion. And with this result, it gives some flow application like a mean cost flow in the unit edge capacity graph in n square time, which is optimal in dense graph. The precise guarantee is this. We have 1 plus epsilon approximation. The total time is n square. Total update time is n square with near optimal query time. And compare with previous work that works against adaptive adversary as well. They have one is that they work with the same bound, but they don't really support path query. But with this, there would be just no application from this work. Another work by Chusoy and Khanna that we base this work on, they only support vertex deletion only, and which is more restricted. And that's why they only get flow application for vertex capacity. By the way, their query time for path query is slower than ours as well. Now, next result, all pair shortest path. The point of this work is that we break an n cube barrier in dense graphs to something like n to the 2.5. This is a precise guarantee, that is, the approximation ratio is not that good. It has constant multiplicative approximation and subpolynomial additive approximation. Now, the total update time is something like n to the 2.5, with near optimal query time, and this work only in unweighted graph only. Okay, but still this still is make a good progress on the state of the art, because compared with previous work, they all need n-cube time in dense graph, even if you allow like bad approximation with some reasonable query time at all, like sublinear query time. So that's a good progress still. So now the outline of the paper and in this talk is that actually the main contribution, the main core of the paper is something called layer core decomposition. This is a thing that we improve upon the previous work, and then it gives us both of our two main results. The second result on our shortest path actually is a combination of two algorithms, one for large distance and another one for small distance. That is, if you want to support query for all pairs that have distance around D, one of the algorithm is faster for large D, another one is faster for small d. By combining both of them, you get the time that we claimed, like something like n to the 2.5, but a bit slower. Now in this talk, what I will tell you will be mainly about this part 2.2. This is because it used some new general idea for algorithm against adaptive adversary that might be more interesting for future work after this. And I will tell you also about the definition of layer core decomposition. I will motivate why it is useful for serving this new idea. I will skip SSSP and large distance APSP. This is because once we have improved layer core decomposition, there is a black box reduction to get a SSSP result that we state from previous work. And large distance APSP just use similar techniques. Okay, so now small distance APSP. Let's do this. The goal is to support query between any pairs of node UV with distance around D, all right? And with this time, like n squared times D. And you should think of D as something small because we are in the small distance regime. And the new idea that you should get out of this part is that it's about routing trees from expanders. You see what I mean by this. The approach that we will use and follow previous work is something called tree cover. This is a framework for decremental APSP that works like this. We will maintain a collection C of trees such that for any pairs that have distance around D, there must exist a tree in the collection that can depend on U and V. That tree such that the distance, the tree path between U and V in this tree is not too far from D. It's like not too high compared to D, like just alpha times D. And now once you can maintain this collection of trees, then you can get alpha approximation APSP. This is because given U and V with this kind of distance, you just return this tree, this distance U and V and its corresponding path. So that's the idea of the framework. And the time from implementing this framework can be analyzed in two parts mainly. First, it's just the time to maintain each tree. And second, is the number of trees that you need to create throughout the whole algorithm. The first part will be quite standard. People just use something like even law tree or monotone even law trees. The second part is the part that people can try to optimize, and we will optimize this using something called core decomposition. So let me tell you what is core decomposition. This is a nice structure that you should try to take this away. So suppose that you have a graph which is simple and have high mean degree delta. Think of delta as something large. So core decomposition says that there are disjoint vertex set x, x1, x2, and so on that we will call core. And each core is well connected in many sense. First, it is an expander, that is the conductance is high. This is a formal definition. And in particular, the diameter is small. Moreover, the edge connectivity inside the core is also high. It's like maximum because it's close to mean degree of the graph. Okay, so that is core. The next thing is that it says that for some vertex that is not in any core, it must still be close to some core. There is a short path of length polylog from V, any node vertex V, to some core. Okay. Moreover, the last thing is that there are few number of cores. So what it says basically is that given a graph with high degree, there are few part of a graph which is core, which we call core. That is, there are few number of them, and every vertex that is not in the core is still close to this core. Okay, now it turns out that we can maintain this structure, which is nice already, almost optimally in the dynamic setting. So what I mean is that now it's just the same setting. You have a graph that undergoes deletion. We will maintain this set of cores by maintaining here. I mean that each core actually only shrink through time. It's the decremental set that shrink through time. Although you can create a brand new core, but each core that you create, once you create it, it only shrink. All right. And each core still have the same guarantee. Every vertex is still close to some core. The point here is that the number of core that you create through time at all is still close to the bound in the static setting. Okay. And that is important. And moreover, the time to maintain this thing is just almost linear time. That's nice. So let's see how to use core decomposition to implement tree cover. The idea is this. For each core X, you create a dummy source Sx, connect it to all vertices in the core, and then you maintain a BFS tree with radius with depth around like d plus some subpolynomial rooted at the dummy source here. And this is what I mean by rooting trees from expander, because the core is an expander. Now observe this. Suppose that you have U and V with distance less than d. Then I claim that there must exist a tree such that the distance from U to V in the tree is also small. And why? Just look at here. If you have U, U must be close to some core. So this is just polylog, and the distance from U to V is D. So by triangle inequality, V must be within distance D plus polylog to the core as well, to this core as well. And you look at this red path, it gives this bound that we want. So this seems like a good thing, except one thing, that is XS, SX is the dummy vertex. It's not in the graph, so we cannot really return this red path. So what we want instead is something like this. That is, once the tree reaches the core, you want some path inside the core that connects the two nodes together. And this path should be really a path in the graph itself, not using some dummy node. And this is exactly what we can do. We can really implement this short path oracle on expanders. So more specifically, given u prime v prime in the core, and know that this core is actually a decremental graph, right? It shrinks through time. But given any pair of vertices in the core, you can return a path of small length in small time, and the total time to maintain this data structure, this oracle, is negligible, is nonlinear. So this is actually might be of independent interest. It's actually later used in other works as well. So, but once you have this, you do get a PSP algorithm. The reason is once you given any pair UV, right, and that have distance around D, you just return this path, the red part here connecting with the path, the black part by the oracle, and the red part here. And the length is like D plus something small. And this subpolynomial term, additive term, explain why we have subpolynomial additive approximation factor in our algorithm, our APSP algorithm. Once we have this is kind of the correctness of the algorithm. So let's look at the time analysis. So let's assume one thing. Let's assume that the average degree is close to mean degree. That is, M is around N delta. We will remove this soon, but if you have this, the time is like before, is the time to maintain each tree. And that we use standard eventual tree that take this much time. And the total number of tree that we create is just a number of core that ever created, which is this. The data factor cancel out, you get exactly this term, n squared d. By the way, in the previous work, this is a part that we improve upon the previous work because they get this bound in over capital D, which is worse when capital D is small and the graph is dense. Now, this is a big assumption, and so let's try to remove it. And to remove this, it brings us to layer called decomposition. Imagine that you have a graph and you want to layering the graph, do the layering of graph by density. So let's say that you keep removing vertices with degree less than h. What you get is that the remaining part of a graph, this remaining part, will have mean degree at least h by definition. You will also have that the average degree of the part that you remove will be less than h. So that's very easy to prove. But let's say that we do the same procedure for log n density level. So that would be log n level. And if you look here, you will have kind of the same thing. That is, if you look at the graph induced by layer I and above, the part that is denser than layer I, the mean degree here will be at least 2 to the I. If you look at the graph of layer I and below, induced by the layer I and below, this part will have the average degree at most 2 to the I plus 1. So what do we have about layer I? It kind of has average degree close to mean degree. Not exactly, but like just some minor detail that I will omit. So this kind of removes the assumption about that the graph have average degree close to mean degree by working on each layer. And now layer core decomposition is exactly it's really like a core decomposition simultaneous. Do the core decomposition simultaneously on each layer. You have a simple graph, and inside each layer, you have a set of cores. The intuition is that in the denser part, there will be bigger core and fewer number of cores. So that is in layer I, Each core is still an expander and it's 2 to the I edge connected. In particular, the size is at least 2 to the I. And the number of core is n over 2 to the I. And what we have is that for any vertex in layer I, it must have like a short path still to some core, but it can have a short path to a core in the above level, in the denser level too. So everyone is still close to some core. That's the point. And then again, we get a dynamic version of this. We can maintain each core only shrink, although you can create a new core. And the point here is that in each level, the number of core over all time is still the same, like before, like in static setting. And we can maintain all of this in almost linear time. And we improve the bound in the previous work here. And once we have this, we will get Apsp from layer core decomposition. And the idea is to use tree cover approach like before. That is to maintain the BFS tree rooted at each core. And let's try to analyze the time. The time on each layer I will be around this n squared d, roughly because this is the time to maintain the eventual tree of depth d. And the 2 to the I come from the fact that Li have average degree around 2 to the I. And now the number of core in Li that is ever created is this. And that gives us n squared d. Except that this is not quite true. The complication is that although you grow a ball from layer I, you grow a tree from layer I in sparse layer, that tree might be overlapping, might go to the denser layer on above layers. And that is why the time to maintain the ES tree might be slower, because your tree kind of span to the dense layer that have average degree greater than 2 to the I. Okay, so that's bad, but the solution is to kind of carefully grow BFS tree from only a safe core that is far away from the dense part enough. You can do this, but it will introduce a two multiplicative approximation factor per layer. We have log n layers, and 2 to the log n is n, so that's bad. But one can fix that basically just by reducing the number of layers in the layer core decomposition to something like constant instead of log n. It's very easy to modify the definition to be like that. You can control the number of layers basically. And with that, the approximation ratio will be still good, like 2 to the k when k is the number of layers. So this is still constant. The additive term is still there. The time will be worse because the density on each layer is not as fine-grained as before. You pay some polynomial factor in n in the total time. So that's kind of the high level how to do Apsp in the small distance regime. And to conclude, we give some progress on the decremental shortest path algorithm against adaptive adversary. For SSP, we break MN bound and still can report path and handle edge deletion that give flow application with edge capacity. Apsp, we break NQ bound for dense graphs. To do that, we use some new general idea that I think is useful. That is to root the trees from expander. We implement this idea in this work using layer core decomposition. In other work that is actually developed after this work, we implement this idea as well, but not using layer core decomposition. But this is just to say that this is really a general idea that I think should be useful in the future. Layer core decomposition is a key object in this paper. It's a nice structure by itself, And we show in the paper how to optimally maintain this structure. So you can look at the paper. So for open problems, obviously this work doesn't give optimal bound yet. For decremental SSP and APSP, can you match the optimal bound attained by the algorithm against Oblivious adversary? That's a very nice goal. Moreover, that there should be more application for this idea of routing trees from expanders, and also the nice structure of layer called decomposition. I think this should be useful outside dynamic graph algorithm too. Now the hard problem is to get optimal algorithm in the directed case, directed graph. This is not known even if you assume Oblivious adversary. So that is very nice question and exciting thing that if you can do anything about it. So thanks a lot.